Today, we're going to pull back the curtain on something we use every single day, but maybe don't think about much: the operating system. And for this explainer, we're leaning on some fantastic research material from Dr. Sudhindra S.G., which was put together specifically to help teachers and educators like you understand and explain this foundational piece of technology. So, let's jump right in. So, let's set the scene. It's the 1950s. Computers are these giant room-sized machines, incredibly powerful for their time. But believe it or not, their biggest weakness was us. A person had to physically load a program, wait for it to run, take the results out, and then load the next one. As the computers got faster and faster, the human operator just couldn't keep up. We were the bottleneck. And that problem is the whole reason the operating system was born. And fixing that problem wasn't a one-shot deal. It was a journey that took decades. This timeline here is basically our map for this explainer. We're going to start in the slow, manual days of the 50s, and we'll walk through a whole series of really clever inventions that got us to the amazing systems we have in our pockets and on our desks today.
So what is an operating system when you get right down to it? Well, the simplest definition is this. It's a program that's designed to run other programs. That's its whole job. It's the very first thing to boot up when you turn on your device, and it acts like a master controller, managing absolutely everything. All the hardware, all the software, all the resources.
Okay, so the first big problem to solve was getting that slow, error-prone human out of the loop. The first major step forward was all about one thing: automation. And the answer was something called batch processing. It was a simple but brilliant idea. Instead of having an operator load one job at a time, they could prepare a whole batch of jobs, maybe on a big reel of magnetic tape. Then, this early OS would just take over, automatically running the first job, and as soon as it was done, bam, it would start the next one. No more coffee breaks between programs. The efficiency just went through the roof. Of course, you solve one problem, and another one pops right up. In these early days, if you were a programmer, you couldn't just say, "Print this." Oh no. You had to write specific, complex code for the exact model of printer you were using. It was a total nightmare. Your program was completely tied to one set of hardware, which made it super hard to write and almost impossible to share with anyone else. This mess led to one of the most elegant and important ideas in all of computing: the device driver. The OS stepped in and said, "Look, programmers, just use one simple command, like print. We'll handle the rest." In the background, the OS uses a special piece of software, the driver, to translate that simple request into the specific, nitty-gritty instructions that a particular printer understands. This idea, called abstraction, was a game changer. It freed programmers to just focus on their apps. All right, so we've automated the workflow, and we've simplified how we talk to hardware. Things are looking good, but a new bottleneck was becoming obvious. The computer's super-fast brain, the CPU, was actually spending most of its time doing absolutely nothing. I mean, think about it. Your program needs to print a page. Printing is a physical, mechanical process. It's slow. While that printer is chugging along, the CPU, which can perform millions or even billions of calculations in that same time, is just sitting there, waiting. It was a colossal waste of computing power. The genius solution to this problem? Multitasking. The OS got a new superpower. It could see that Program A was stuck waiting for that slow printer, and it could say, okay, instead of waiting, let's pause Program A for a millisecond and let Program B use the CPU. By switching back and forth between programs thousands of times a second, the OS creates this incredible illusion that everything is running all at the same time. So how does the OS actually pull off this juggling act? Well, every program, or process, is always in one of three simple states. It's either running, meaning it's actively using the CPU right now. It's ready, meaning it's in line waiting for its turn. Or it's blocked because it's waiting for something slow, like a file to load. The moment a running process gets blocked, the OS instantly grabs a process from the ready queue to take its place. Doctor's material uses a perfect metaphor for this. The OS basically becomes a traffic cop for the CPU. There's a special component inside the OS called the scheduler, and its only job is to direct this flow of traffic, deciding which program gets to go, when, and for how long, making sure that CPU is always as busy as possible. Okay, so multitasking is amazing, right? We can run lots of programs at once. But this created a brand new and very dangerous problem. All of these programs now have to live together and share the computer's main memory, its RAM. And as you can imagine, that can get very, very messy. I mean, just picture it. You've got 5,
10, 20 programs all crammed into the same physical space. What's to stop a bug in Program A from accidentally writing data right into the middle of where Program B is working? The answer back then was nothing. One badly behaved program could scribble all over another one, causing crashes, or even worse, corrupt the operating system itself and bring the whole machine down. Total chaos. The solution to this was an absolutely ingenious concept called virtual memory. On the left, you see the messy reality of physical RAM. It's fragmented, it's shared, it's chaotic. But on the right is the beautiful illusion the OS creates for every single program. It tricks each program into thinking it has its very own private, perfectly organized stretch of memory, all to itself. And behind the scenes, the OS is the master magician, mapping that perfect illusion onto the messy reality. So, how does the OS enforce this illusion and keep everyone in their own lane? With something called memory protection. Think of it like a strict security guard, backed by the computer's hardware. If any program tries to reach outside its assigned virtual space and touch memory that doesn't belong to it, the OS stops it, cold. This is the absolute key to having a stable computer. And this quote just nails it. It's that tidy illusion that changes everything. It's the reason why you can have a dozen apps and 50 browser tabs open, and when one of them crashes, it doesn't bring your entire system down with it. It isolates the problem and keeps everything else safe and stable. So, we've automated jobs, we've tamed the hardware, we've made the CPU a master juggler, and we've organized memory into private little universes. Now, let's look at how all these pieces of the puzzle came together to build the operating systems that we all know and use every single day. You know what's really interesting is that all of these core ideas, multitasking, device drivers, virtual memory, they weren't invented for our laptops. They were first developed for these enormous, super expensive mainframe computers that lived in universities and big corporations. These were called time-sharing systems. And they were so powerful that dozens of people could use one computer at the same time from their own terminals. And this table here really puts the journey into perspective. When the first personal computers came along with operating systems like MS-DOS, they were actually a huge step backward in terms of features. As you can see, MS-DOS couldn't multitask, and it had basically zero memory protection. All of the amazing progress over the last 40 years has been about packing all of those powerful mainframe-era ideas into the device that's sitting right in front of you. So, why does all this history actually matter to you? Because every one of these innovations directly impacts your daily life. That stability you take for granted, that's thanks to protected memory. The fact that you can listen to music while you type up a report, that's multitasking. The reason you can plug in a new mouse and it just works, that's those managed device drivers. This stuff is the invisible foundation of everything we do with our computers. And at the heart of pretty much every modern operating system is a fundamental design, first pioneered by the Unix system, that splits everything into two core parts. Think of it like two separate worlds. You have the kernel, which is the protected, super secure inner core that handles all the critical stuff. And then you have the user space, which is the outer world where all of your applications live. This separation into two parts is a huge reason why modern operating systems are so robust and secure. So when you boil it all down, the story of the operating system is really a story of brilliant problem solving. Each innovation we talked about, from batch processing to virtual memory, was a clever solution to a real, tangible bottleneck that was holding computing back. It's this incredible, invisible foundation of solutions, built up over decades, that makes everything we do today possible. And that brings us to a final thought to leave you with. The OS has always evolved to solve the great problems of its day. So as we head into a new era of computing, with AI, with quantum computers, with massive global systems, what's the next big bottleneck? What is the great problem that the operating system of the future is going to have to solve? It's a really fascinating question to think about. Thanks for joining us for this explainer.